Welcome to Study Loop.
So we want to let x be the length of the north and south walls, y is the length of the east and west walls, and then z is the height of the building. So the heat loss is going to be given by H equals 10 times 2yz plus 8 times 2xz plus xy plus 5xy. And what that's going to end up giving us as a result is 6xy plus 16xz plus 20yz. So conceptually, we don't like the fact that we have three variables. It's easier to get it in terms of two variables. So if we know our volume is xyz equals 4,000 meters cubed, we can solve for z and end up getting that that's 4,000 over xy. Now we can plug that in, and now we have a function h of xy, which is going to be equal to 6xy plus 80,000 over x plus 64,000 over y. Since the height must be at least 4, we know that z is greater than or equal to 4. So when we solve for y, we get that y is less than or equal to 1,000 over x. Then we know that each wall must be at least 30 meters long. So x is greater than or equal to 30, and y is greater than or equal to 30. So that means that our domain is going to be the set of all xy, such that x is greater than or equal to 30, and y is greater than or equal to 30, but less than or equal to 1,000 over x. And it's going to look like this graph right here, which starts up here and then tapers off and goes down here. So that's our domain. Then for part B, we want to take partial derivatives. So we have h partial derivative of x is going to give us 6y minus 80,000 over x squared. Partial derivative of y is going to give us 6x minus 64,000 y squared. And then when we set these equal to 0, we can now set them equal to each other. And we get that y equals 80,000 over 6x squared. So plugging these values in and substituting our values, what we can do is get that y is equal to, x, because we'll substitute this in. So we're substituting this in for y and solving for x, and we get that x is equal to 25.54, which then allows us to find y once we plug it in, and that's going to give us 20.44. Then using those values right there, we see that our critical point is 25.54 and 20.44. Using that critical point, what we end up finding is that we get a maximum value, and that is going to be h of 100 over 330, and that is going to be equal to 10,533. That's on our first surface. So if we go back here and we look at all of our surfaces, our maximum on L1 right here, which is that surface, is going to be that value. Then we want to look on L2, which is this curve value right here, L2. And we get that h of 100 over 3 is equal to 10,587. So that's slightly larger for our maximum. And then we find on L3, which L3 is this surface right here, what we end up getting is h30 100 over 3 again, which is the same thing, 10,587. And then lastly, we see that this is right here, our maximum. So the absolute minimum of h is going to be 10,200, and that's h of 30 right here. And then we want to find the height when this is the case. So we have z equals 4,000. This is our equation from before, 30 squared, and that's going to give us approximately 4.44 meters. So what that tells us is x equals y, which equals 30, and z equals 4.44.